Hey everyone, a few months ago I decided to build an SQL engine from scratch as a learning exercise, and now that it's done, I wanted to share the source code and just explain what I've done. So without deliberating, let's see what we have. So if you do download the source code, it comes with a few tables just to play around with. So if we do select all from master catalog, these are the tables in our database, in addition to the master table which contains this data, right? So we can do things like, select age, username from users where, not age, age less than 30, order by age. And so here we are, we have our age, our username from our users. So actually, our users are select all from users. These are all our users. Um, and then we can do things like update, users set username equals marky mark or marky mark, where username equals say Lila, and then if we just do another select all, then we have that change. If we end the process, start it back up, and we do another select all from users, then that change is done. So we have that. We have delete, insert, create and drop table working. So that is like that is what we can do now. Our project is very much split into the sort of front end and the back end. So the back end is the sort of execution of queries, and the storage engine. And then the front end is actually parsing this SQL, passing it and turning it into a sort of bytecode program that we then execute in the virtual machine. Now, I'll get to all those bits, in particular, but um, our backend is actually a lot more complete than the front end. So that's the sort of subset of SQL that we can actually like parse and create queries and compile queries for. But our backend is actually a lot more capable. In fact, it's sort of capable of doing more or less every sort of SQL query. And so to show that, I've just hard coded a few like demo programs that sort of show that capability. So if we do something like get demo like, so the like expression is sort of select all from users where username like, and then there's this sort of string that you can pattern match on. So if we do demo like Anne, so now we have the users where their name contains an Anne, right? We can do demo join. So here's the join expression. So select username, city, order by, total from users, join orders on user by user ID equals order dot user ID. So this is a join expression or join query that we can do. And another one is demo group. So group would be select city, count, sum the age from users, group by city. So that's a sort of more complicated aggregate query. So those demos are just to show what our actual like execution layer, like back end of this project is actually capable of. But our sort of front end, so to actually parse this and then to turn that into a query, is something our front end can't do, but the back end is very much capable of. So that's what we can do. Now, just a quick sort of high level overview of the project. So we have our sort of SQL string input that is passed into an abstract syntax tree, which is then sort of semantically analyzed. So for example, if we want to do select all from users, does the user table exist, right? And we can resolve certain like types. So hey, does it make sense to say is the username greater than 5? Are those types compatible? And then sort of resolving like data that makes it easier to compile with. So you want the column age. Well, age is the third column, right? So give actually match that to the sort of ID column 3. We have our catalog, which is our in-memory copy of the master table, which contains things like the actual schema information for individual tables, right? We have our compiler, which then we can actually take this abstract syntax tree with its sort of semantic annotations, and we can turn that into a bytecode program that we can then execute in the virtual machine, which itself operates by manipulating the sort of storage layer via cursors. The storage layer is mainly just the B+Tree, which is a way which actually manages organizing the data, the table and index data, which itself has a sort of abstracted view of the file system provided by the pager, right? The pager sits on top of the OS layer, which is just a sort of cross-platform layer for things like read, write, and seek file operations. And that's really it. So that's the high-level overview of the project. What the project can do. And now let's get into each individual part of this project. So I really want to build from the ground up because I know a lot of people watching this, like myself, will be self-taught, and or have only worked professionally in a sort of high-level programming language. So further, the kind of problems that we actually have to deal with and the solutions we have for those problems have certain like prerequisites to understanding, right? So I think the first thing to cover is what is the difference between a high level and like a low level programming language. So like what is the difference? Well, I think like in short, the difference is in a low level programming language you have to care about the actual like semantics of the hardware. Like what does that mean, right? So as an example, I have two equivalent functions here in a high level and low level language, right? JavaScript and C. And then out here is the actual output, the assembly instructions, the computer instructions that are going to be executed on the chip in order to run this bit of functionality. Now, with our very simple square, function in JavaScript, takes a parameter, multiplies it, returns a result. We have like, I don't know, like 40 plus assembly instructions, right? Compare that to C, where we have like 5, and this is to say nothing of like optimization. If we put bump up the optimization, it goes down to like nothing, right? So like, why is this? Well, computers only really do a few things, right? Like they load and store data. They you can do arithmetic on like particular particular slots of data, and you can do conditional jumps, and that's like like more or less like it, right? Those are the instructions that like a CPU can execute more or less. And so if you want to do things like create if you want to do things like have an object like so, and have a member have a member for that object, and be able to set it to an arbitrary string, but then just set it to like a number, and then to multiply an integer by something that could either be a number or it could be a string, and for it to just work, for it not to throw some sort of compile error. In order to do that, you need a lot of infrastructure, because there is no machine instruction to do this, right? That needs to be built as sort of infrastructure, and that's what that's what the V8 sort of runtime is doing, right? It will handle the allocation of this memory, where it is, in the actual computer's memory. Where is it when you set the variable to something else, and this memory is no longer like actually like reachable and used? That memory is freed. That's handled by the runtime. Whether or not stuff is a number or a string, and then what the result would be, even if it is a string, that's handled by the runtime. Even though that there is no assembly instructions to do this, it's the actual like C runtime that is handling that, and that's sort of what a high level programming language is. It means you don't have to think about the particulars of this sort of stuff. Whereas, in C, if we want, we can't do that because C is essentially just a high level assembly. It's just like assembly with a lot of like syntactic sugar. If we want to allocate space for a variable, we need to be explicit about how much memory that variable will take. If it's an integer, it will take 4 bytes. If we want 32 bytes for, an array of integers, we have to say, all right, we want 32 bytes. And that's the sort of stuff we have to do. And if you try to, if you try to set, a 4-byte slot as a string, it's just not going to work. So that's really the difference. In a low-level language, we have to care about the actual like semantics of how things are laid out, in memory. And we have those constraints. Now, why do we even want to use a low-level programming language then? Well, it's because, in a database, like we actually need that low-level control. I mean, if all you want to do is like build a web app, then this is all like just superfluous like control. But for something like a database where we need absolute fine-grained control over how the bytes are laid out, both in memory but also like on the disk itself, and it needs to be fast, right? Then we need that control. And so I think that's the sort of mental model that is sort of that will be sort of sufficient for like moving forward. So we need to be very explicit about how we work with and operate on the bytes in memory and on the disk. Now, in C, we don't have objects like you do in JavaScript. What we have is structs. And what structs are a way to group other data types in a sort of custom memory layout. So as an example, we have the user struct, and we define that as 4 bytes for the user ID. After that, we have 32 bytes for the name. After that, 32 bytes for an email, then age, then city, right? And then so when we actually instantiate that, right, in this example, putting that on the stack in our function, what we do is we're allocating this amount of space in memory. And this particular instance will get an address, a sort of start address where that memory for that instance starts. Now, to visualize that, here's an example of it actually laid out, right? So, and memory and files and such, the actual abstracted view that we get when we're writing user programs that the OS gives us is that of just a big contiguous array of bytes, right? That's what we can think of memory and files as. And so this is, imagine some memory in the in the actual memory that we have. This is the space required for our user struct. So our ID is here. That's the first 4 bytes. After that, we have the next 32 bytes. After that, the next 32 bytes. After that, 4 bytes, etc. Now, another sort of key thing to note is that like the CPU can't actually just randomly pull these things in. What it does is it takes that memory address that we have when we allocate some memory. It takes that initial address of that instance, and then it will add however many bytes it needs to, like in terms of how it will increment that address until it is at that particular field. So if we want to access age, and we want to pull that age that actual age, those bytes into the CPU, what actually happens is it looks at this particular instance, its memory address, and then it will add the various offsets that it needs to get to that field. So if we want to access age here, we have our base address, and our field offset is the total amount of bytes that all this other data takes up. So in that case, it's 68 because we have 32 bytes, 4 bytes, etc. And then we get to our final address where this memory actually is, which is 0x44. To access ID, the base address plus 0 bytes because it's at the front, username plus 4 bytes, etc. Right? So that's actually how accessing specific members works. In C, what happens is when you compile, this idea of structs, that all goes out the window and it just becomes raw sort of pointer arithmetic. And the same is true of arrays. So we can actually look at the schema of our users table, and we can see it's the same as our user struct. But the thing is we don't have the user struct in our code base, right? Like, how could we? We need to be able to support arbitrary combinations of the actual data types that we support. And furthermore, how are we actually doing like queries on particular fields? If we need like the particular offset of a certain field and we need to be explicit about that, how can we do things like select age when we don't know that age is even going to exist before we compile? Right now we have no better way to do it than just doing it like this, where we have select users where age greater than, and then we can parameterize the age. Great. So how do we get around this? How do we actually do like dynamic like programming in C? And I don't mean like dynamic like leak code, but like just generally like not knowing the types and the operations ahead of time. So let's actually look at our implementation. So we have a struct defining our relation, our table. It has an array of attributes, columns, and that attribute has 32 bytes for a name, and then it has a data type. And what a data type is it's an 8-byte integer that can encode information about a particular type within it. So, for example, it can encode that you have an integer, that integer will require 4 bytes, and that it's signed, or unsigned. It can, a type can be, okay, this is a string type, and this particular string is 32 bytes, or it's variable length and has however many bytes that encoding says it has. And then what we can do is we can work with this particular value and take in arbitrary memory addresses and then do some operations such that we can actually do specific operations at runtime. So for example, here we have comparison. So we take in two arbitrary memory locations, we take in a data type, and then depending on that data type, we reinterpret the byte at those memory locations as that particular data type. So if we say that, okay, well, we have two 4-byte unsigned integers. Here's the type. Here's the memory locations. That will reinterpret those the bytes of those memory locations as 32-byte unsigned integers, and then do that here. So then the way this would work when you create a table is you would pass in the various columns that the table is going to have. You'd pass them, and then you would push those onto an array and create an array of data types. So that then, if you wanted to work with a block of memory that was the column like we saw with a struct, you wouldn't have that struct definition as the actual struct definition, but it would be in that particular layout, and then you would use the information encoded with these data types in that array of data types to then decode that memory. And we would support all the different operations you'd need. So we have our comparison, but then we'd also have like arithmetic. So again, you take in arbitrary memory addresses for the two sources and the destination. You take in the type, and then you reinterpret those that memory as those types and do the operation. And so yeah, this allows us to create these types at runtime and work with them and do our sort of offsets. For example, if we want to access, if we have a block of memory that has the same layout as our user struct, but we don't have the user struct, if we want to access a field, it's a matter of counting all of the entries in that array, all of the data, the size of the data types in that array, and then taking that pointer that begins the memory and then adding it. So we essentially do what a compiler would do at compile time, but we do it at runtime. And that is how you get this sort of fully dynamic C code, and that's how we will support arbitrary combinations of data so that we can work with them. We can do arithmetic, we can do comparison, and actually, you know, loading specific fields at runtime. So to go back to our example from earlier, where we had this, you know, hard-coded query because we thought we needed to know the actual layout ahead of time, we can turn this into something more generic. So if we can turn it into select where, you know, single condition, we can get rid of that, and we can pass in the table name. You know, we can pass in the attribute name, you know, the column name. We can give the memory location of the thing we're comparing against. So, you know, where age is greater than 30, we'll pass 30 into, you know, an integer and then return the memory location of that integer. And then we'll give the comparison op, so, you know, greater than. Then we do, you know, table equals, you know, tables dot get. This is just pseudocode, right? But we have to get the table, and we say, okay, well, we know the table, you know, size, and then we go, you know, the actual field is table dot, you know, get, you know, attribute name. And then instead of users, we'd say, okay, well, tables, you know, table dot rows at I. And then we would go, okay, well, type compare, you know, field dot data type, the, you know, memory location of that, of the beginning of that row. Well, actually, would it be, no, it would be the beginning of that row plus, you know, the field offset. So like we talked about with the compiler, where we have, you know, we have this sort of struct definition, and we have the base address, and then if you want to access a specific field, you would apply the offset, which is the actual memory, the memory in between that field and the base address. So the beginning of the row plus the field offset, then we would pass in the memory, and then finally the operation. And then whether or not this returns, you know, okay, well, it's our operation, so it will return, you know, like 1 if it's true and 0 if it's not, in which case we would, you know, print the user. So this is just, you know, pseudocode, but it's more or less, it's pretty much exactly, you know, what we're actually doing. We, you know, can parameterize based on the query, what is the table, you know, select from users where age, that's the attribute name, is greater than 30. 30 passes to an integer. We give that memory location greater than, that's the comparison op. We get the table, we get the field, we do the comparison by passing in that field's data type, the location of that particular row. We'll loop over, and then we'll add from the beginning of that row the field offset, and that's how we do it. And so yeah, that is pretty much, you know, how we're doing these conditions on structured data, but not knowing the structure ahead of time. So we're in a lot better position than we were, but we're still quite far off from being able to do everything that, you know, SQL can do. So for example, like select, you know, username, age from users where you know, not age less than 25 and age less than, you know, 40, order by age descending. You know, we've selected what columns we want. We've selected what conditions on which columns, and whether or not the results of two conditions can, you know, actually result in whether it passes or not. So, and we're pretty far off from that from here. So what we actually need is a way to make this more, you know, composable. Right, so what do we need, right? Well, we need a way to do to load and sort of store and move data around. So, you know, we want to load values like, you know, 25, where age is greater than 25, but we also want to load the particular columns to do those conditions in, right? So the age column. we want to do like comparisons and arithmetic on those values. So for an update, like if you had a table for like students, and those students had like a year, like a school year column, and you might want to go, okay, well, every year we say update students set year equals year plus 1. So you want to do like general arithmetic on it, and you want to do comparisons for, well, okay, well, is the age greater than 25? And we want to take the results of those comparisons, and we want to put them somewhere so that then we can do an and on those two values, and then put them in another sort of place, so that then we can conditionally do something like, okay, well, if the condition is met, then print the row, and if it isn't, do something else. And a way to sort of actually move through the table, sort of iterate through the table. Perhaps a way to sort of like do the same logic over and over again, but like with a different input, right? With a different row. Well, when you say all this, it really sounds like what you actually need is a computer, right? Like what we actually need for our database to work, to handle arbitrary queries on arbitrary data, is a computer to do all this like runtime interpretation. And that's exactly right. Like that's what a virtual machine is. A virtual machine is a computer written in software, and it can be a one-to-one mapping of like the actual chip, right? Like you can write a virtual machine for, this is an x86 virtual machine, or you can write a virtual machine that does something like far more simple or specific. Our virtual machine in the database, it has general purpose computation, but then it also has like database specific stuff. So to get an idea about how a virtual machine works, I have this visualization. So what we have here is, it's a very simple compiler into a bytecode and virtual machine for a very simple programming language, right? So what we can do is we can go x equals 10, y equals x plus 5, if y is greater than 10 or greater than x, we can print y, right? So this is our program. When we compile it, this is our abstract syntax tree. This is the tree representation of our program, where we can see we have an assignment to a variable x, which is 10. We have an assignment to y, which is a binary op, which is a plus operation, an identifier x, plus the number 5. We have an if statement with a condition, which is a binary op of greater than, between y and x, and then we have a print, and then that's its parameter. And so then the bytecode program that is compiled from that is that we load 10 into register 0, or just load it at all. We move register 0 into register 2. It's not very good bytecode, but we load 5 into register 3. We then do an add operation, and we put that in register 1, I believe, and then move 1 into 5. Again, this is really terrible bytecode, but it works, right? And then we do a greater than operation between the values in these registers, and then depending on the result of that, we do a jump. If 0, we would jump to program counter 10, which is the end. Otherwise, we would let this block execute, which would print it out. And so if we run this, we print it out, right? So let's reset and step. So we load, we add, we move that result, we do a greater than, and put the result in somewhere. If it's not true, right? If it's 0, we'll jump, but we don't. It's not 0, so we don't jump. We execute this print, and there you go. If we change this operation, we recompile it, and then we step through it, then it's a less than that. That will be true, and so it will jump to halt. And so, this bytecode, this is going to be an array of instructions, and so a jump will basically take, okay, is this true? And if it is true, then jump, then move the program counter, the actual thing that's like, okay, well, this is the instruction where we're on, move that to a different to a different like index, to a different instruction in that array, right? Which could be the halt instruction, which will come at the very end. And so we can do all kinds of things. So we can go, okay, well, while y is greater than x, we can print y, and we can compile that. Then we can step, and then we're just going to print y. We're going to print 15 forever, right? We're just, every time we do, is y greater than x? Yes, it is. So we don't jump. So we print y, but our loop is an unconditional jump to the beginning of that block, where we then do the condition again, and if it's false, then we jump back, right? So we go, so we get to the end of the loop and we jump, and then we do the comparison, and if it's 0, then we would jump to the end, but it won't be. If we do y equals y minus 1, and we recompile that, then we can step through it, and we can print 14, 13, something, something, and we can just run that in a loop, and then it's no longer greater than x, so it stops. And so that's the kind of that's sort of an idea of a virtual machine for a very simple programming language, but it's really all the same concepts, right? Similar to how we saw with machine code, there's like loading and storing data, there's comparisons, there's arithmetic, and that's like, and then there's jumps, and then that's more or less it. What we need in order to do our general purpose computation, to do things like selecting only certain columns, doing comparisons on arbitrary columns with arbitrary data, and then chaining the results of those with ands and ors. The way we do that is by building a virtual machine capable of general purpose computation, but with specific SQL parts as well. And then we transform our SQL queries into a bytecode program that we then execute in our virtual machine. So to just see our implementation of the virtual machine, it has a few things. So we have our actual VM state. So we have an array of VM instructions. We have our program size, we have our program counter, what instruction it's at, and when we do a jump, we say, okay, well, we move the program counter, right? We might move it to the end because it's a halt and we're done. We might move it back to the beginning of a block because we're looping through all of the rows in our table. We have our registers. Remember, registers is where we put these intermediate values, and this is an array of type values, which have like a data type, and then they have the memory for that data type. We have cursors and the result callback. We'll come back to cursors in a bit when we talk about the storage layer. But the long and short of it is that's where we're getting like our like table data from, and how we're like iterating over it. And our result callback, we're printing the result, and so on and so forth. So we begin with our sort of execute. We reset the state. We set the program. And we begin looping over our instructions. And every time we execute an instruction, either it's a jump instruction where it sets the program counter, or it's just a regular instruction when it will increment it. Our actual VM instruction itself is, we have an opcode, for what we'll actually do, and we have various parameters for it. So we can parameterize it. We can say, okay, well, where is age greater than, etc. We pass that. We set. We allocate that memory, and we set, okay, well, this is where the memory is, so that we can load it into the VM, into the register. And so in our step function, this is what we'll loop over the program, and we just have, it's just a big switch case. That is what it is. It's just a big switch case of opcodes. For example, when we go to do arithmetic, we will have our destination reg where we want to put the result of the arithmetic. We will have our left and right register where the operands are, and we'll have the various op. These macros are just to, like, I have a lot of macros to actually create and access the parameters of these instructions. These are just because they need to be in sync from in the VM and the actual where we can do the compilation. They need to be in sync, and because I'm the only the only like guy working on this, it's just easier to have macros to sort of keep that access the same. So but yeah, so this is just the parameter 3. What operation is it? We then we've already loaded those two values in those registers. We get the type, we ensure they're the same. We allocate memory for the result, and then based on the operation, we do the arithmetic. We put in the type, we put in the result location, and then we put in these two arbitrary memory locations, and then that's the result of an add instruction. And then when we would actually, if it's if this was a comparison instruction, we would look at that result in the next instruction, and then we would jump to some other part of the program depending on that result. If it was if it's greater than, if the age is greater than 25, go and print the result. Otherwise, increment, move to the next row and do the same again. So that is our execution sort of model. We pass the user's SQL string into an abstract syntax tree. We then generate a bytecode from that. So we see select, username, email from users where age is greater than 20 and age is less than 40. This is our abstract syntax tree. We have a table, users, we have the columns we want. We have a where condition, which is a binary op, which takes the operands and its two operands are themselves binary operations, in which we sort of we load those literal values with the query, and then that will be transformed into a bytecode. So bytecode, select username, email from users where age greater than 25. We can see this bytecode program that is eventually generated from this query. So we open a cursor, which I'll get to when we talk about storage layer, but it's just think of it as like opening a table to scan. We rewind to the start of that table. So we go to the first entry. We jump if we're at the end. So if the table's empty, and if we round to the start and the table's empty, we're at the end. So we would jump to program counter 12, which would close the cursor and halt program. We load the first column of the first row. We load our 25, our value 25. We test against it, and we put that result in R3, so register 3. Our jump if looks at register 3, and if it's false, then we go to program 10, which would skip this part. So if our age was if our age was less than 25, it would skip to this part. If it is over 25, then it would load these columns, and then it would in these particular registers 4 and 5, and then it would actually output the columns at registers 4 through 5. Then it would step forward. So we're at the first entry. It would step forward to the next entry, and then it would go to an unconditional jump to program counter 2, and then it would test. The result of the step is put in R0. So if we're once we step forward, if we're at the end of the table, that result is put in R0. We then go to and we test our 0, and if it's false, if we're at the end of the table, then we'll do a jump to 12. And so then this will loop over. So we call next and we process a row in a loop. And then depending on whether or not that row satisfies our conditions, whatnot, we load the columns we actually want, and then we call, okay, output the result. And so if we can see this, if we put debug on, dot debug, and we do, select username, age from users where age is greater than 25, or 35. And this gives us a lot of, I think I went a bit overboard with the debug printing, to be honest. But this gives us, this gives us the program that was created. It's going to be executed, and then this is the execution trace, right? So we open our cursor to the table, we rewind to the start, we're not at the end, so we continue to program counter 3, we load the first column, we load column 3 of the first row, that's 70, we load 35, we test is 70 greater than 35, it is, we're going to jump on false, but we don't because it's not false, so we continue, and then we load the other two values, or we load the two columns rather, and then we output the result, and then this is the result. So we immediately output that result, right? And then we step forward, and we put the result of that. Are we at the end of the table? In register 0. It's 1, so we're not at the end of the table. And so then we jump to program counter 2, and then we do a jump on false. It's not false, so we continue, and then that's the loop. And then this is the loop for going over the rows. And I put quite a few rows in here, as you can see. And that's it. And that's the execution of a query. And that's showing sort of the general purpose, computation that we do. And we can still show off our say demo join again. So this is going to be really long. Yeah, it's actually going to be stupidly long. But what this join is doing is it's gonna, it's just a very naive double loop like join. So it will, for every row in one table, it will loop over all of the other entries in the other table, and it will test against that condition. And if it's true, then it will output the row, and it will select the various columns you want. So we open two cursors on two tables, rewind to the start of both. For the first column, or for the first row of the first table, we loop over all of the other rows of the other table, and we see, okay, is this condition true, or do we have a corresponding row? If we do, select those particular rows that we want, and output the result. And that's what a join is, right? And the same, and with our aggregate queries, it's like, we count data and we increment, like, okay, well, have we seen this before? And actually we'll get to that, because that actually touched on something else in a bit. But yeah, that's the general execution model, and why we need a VM, basically. So the problem statement thus far has been, how do we do arbitrary combinations of operations on arbitrary data? And our VM is the solution to that. The second half of our sort of problem statement for our database is that of building the storage layer. Now, so what do we want out of the storage layer? Well, first we want a way to do efficient file I/O in the context of just like a database, not just an SQL database, not or a graph database or a Mongo database, just a database in general. Now that sounds quite vague, and I'll get to it when we talk about the pager specifically, but that is something that we want to do. We want transactions. We want to be the ability to wrap any sort of mutation of the database in a transaction, such that in the event of a crash, we can roll back and we can get the database to its last sort of valid state. Or if a user wants to roll back for some reason, they can do that as well. So wrapping any mutations of the database in this transaction mechanism, we want that. We then want actual specific storage structures that give us different performance characteristics. So if we want to store a blob, a 4 megabyte blob, we wouldn't put it in a B+Tree. It would be horrible, right? We would store it in particular sort of blob storage. If we wanted just a key value database, if all we ever wanted to do was get keys and get values by keys, would a B+Tree be the right answer for that? Well, it wouldn't be horrible. It would be fine, but it wouldn't be optimal. Hash-based storage would be optimal for that. But if we want to do complex queries, if we want to do things like range queries, then a B+Tree is absolutely optimal, and that is why it's the sort of quintessential data structure for SQL. So that sits on top of our page or our specific storage structures with their own sort of characteristics. And then finally, on top of that, we have the Cursor Abstraction, which unifies access to these things. If we had hash storage and we had a B+Tree storage, we would have a cursor that would provide the interface to actually iterate over, move through these storage mediums, seek to specific keys, and then actually mutate the particular entry that we're on, and that is what the VM uses to interact with the storage layer. So that's an overview of the storage layer, and now let's look at the actual specific parts. So the operating system provides read and write functions for file I/O, where it can read a variable amount of bytes from a arbitrary position in a file. The thing is that operating systems don't actually do this under the hood. They don't read the amount of bytes you gave it. It will read whatever multiple of its sort of configured page size is. If you go and you ask, hey, give me 3 bytes from this file, it doesn't read 3 bytes. It will read its configured page size. Historically, that's been 4K. On Mac, I think it's 16 kilobytes. So it will go and actually read that amount of data from your drive, and then just give you back however much you asked for. And so, in the context of a storage engine, not specifically SQL, not or any other storage engine, in just the context of just a storage engine that has to do efficient file I/O, it doesn't really serve us to think about to work with files as sort of byte-oriented structures. Rather, it serves us to think about them as sort of page-oriented structures, to think about them as just a big array of pages that we can then index into. Give me page 4 is give me for the data at 4 times the page size. That's the offset in the file, and then read a page. So if we we see in our pager, instead of just doing our regular file seek and file read, what we do is we say, okay, we'll read this page. So here's the page index, here's the data you're going to read that into. And so we then seek to that position of a file, and then we read that amount of data. Similarly with write, we seek to that position, we write that amount of data. And that's a simple pager right there. And then the layers above it will have that abstraction of the file system. They just need to think about what index is the page I want, in. So to see this actual abstraction in action, here we have just a simpler example than seeing the B+Tree. Here's just blob storage. So we have our blob node, which the struct, the actual data layout, takes up exactly 1 page size. With just the raw byte data, but then also the metadata like where this node is on the on the file, such that the index times page size gives you the actual byte position on the file of the beginning of this node. Then we have the next, which is points to the next actual index in a sort of linked list. So if we have just a big blob of data, we'll just store the parts of data in a linked list, and then when we get to the end, the next will just not be set, right? It will be like 0. And so actually creating a blob involves getting the data, or like being passed the data, being passed the size of it, figuring out how many nodes do we actually, how many pages do we actually require to store all this data, and then going and then creating that page on the database file, writing that data to it, and then creating another one and linking it to to the in that linked list, and then similarly accessing it, also like deleting it. For example, you take the first that sort of first entry in the linked list, the index of the first entry. You get the particular node. You say, okay, pager, give me read this page and get me it, and then we get the next whatever's next in there in that linked list, and we call delete, and then we just do that while we're not at the end, and then that's the block deleted. Similarly, get is what's the first page, let's allocate all the memory we need for it, and just follow that linked list by indexing into the file. So again, it's the file system becomes an array of pages, and that's how higher level modules see it. So what else do we want from the pager? Well, having to do a file IO every time we want to get a page isn't the best. There's probably a lot of circumstances where we actually want to keep the sort of same pages in memory for a period of time, and that actually certain pages are required more often than other ones. So we want really some kind of caching layer. So that's what the pager provides. In this one, we have just an LRU cache. So when a page is accessed, it's moved to the front of the queue, and if the cache is full, then the last one is kicked out, and every time someone accessed it, it's moved to the front, and then that gets pushed down. So that keeps the most recently accessed pages in memory. But depending on your workload, cache heuristics can vary tremendously in how effective they are. And in fact, like in SQLite, I think the cache, certainly the caching heuristics is a pluggable module. So we have this caching layer, but that's agnostic to the caller, right? The caller doesn't know whether or not the page it just got came from memory or came from an IO. The interface is the same, right? We call pager get. We call pager get. We get or load it. So we say, okay, we have a mapping to like page indexes to positions in our cache, and if that mapping has the page index we asked for, then we just return that slot after moving it to the front of the cache. If it isn't, then we find a free slot either by picking an empty slot or by evicting the last one. We then read that particular page and read it into our cache slot, and then we move it to the front, and then we return it. But that is all under the hood to the caller, right? The caller just sees page get and no other detail. So great, now we have a caching layer. What else do we want from our pager that we want to handle here as opposed to in higher level modules? Well, right now, if we delete a page, or in the case of like a blob, several pages, if it's a B-tree, we'll be doing a whole load of pages. Right now, that will just leave like a gap in our database file. So we want a way to actually track the pages that we've deleted so that when we want to like allocate a new page, we actually don't append to the end of the file. We actually give back a page that's been deleted, right? An index of the page that's been deleted. And so what we can do is when we do actually delete a page, we can reinterpret that page as a free page, our free page structure, which again is exactly page size bytes. And we can set the sort of salient information, which is the sort of, okay, its index, it's already set its index. The previous free page is the current, is the head of the free list. That's tracked by our root at page 0. Page 0, or like the index 0, acts sort of as a null here because our root, like our page of root, is at index 0. So if something is like 0, it's like null. So our root maintains, okay, what's the head of this free list? This is the head. Okay, well, we're deleting a new page, so let's add it to the free list by, okay, well, that's the new head, but the previous head now attaches to it. So, now if you want to then allocate a page, if we want to say page new tries to take it from the free list. If it's 0, okay, then we have, our database is sort of block by block full. So no, we have to append to the end of the data file in order to allocate a page. So that's a way in which we can track the empty slots in our database file, and then make sure it's not any bigger. When we're asking for a page, we never append to the end of the file unless we absolutely need to. Now, this doesn't handle the case where maybe we delete huge sort of swaths of our database and don't have any immediate desire to like add more data to actually fill up those empty slots. This doesn't handle that, right? The problem is that our page doesn't really it doesn't actually interpret the data of the pages. We have this base page we have this base page where we say, okay, well, look, if you're going to have a page in this database, then you need the index. You need sort of the index in the database file in the first 4 bytes, and that's for transactions, which we'll cover in a minute. But the rest of it can just be whatever, man. Like, whatever, man. Like you put there what you want, and so we don't know what the actual contents of these pages are, and so for something like a blob where they actually have links, it's a linked list, these pages are linked to each other by the index of, offset in the database file, or even worse in the B+Tree, where we have all of these different pointers that pointing to indexes in the database file. We can't just compact the database file. We can't just take what's at the end and fill it in these empty slots, because we don't know what the data is, and we wouldn't know how to reattach all of these different connections. And so if there is a compaction mechanism, that would have to be implemented by a higher level module that actually knew what its own relationships were. But we can't do that in the pager. So that is the limitation. Okay, so last but certainly not least with the pager is transactions. So the ability to wrap any sort of mutating change, whether it's allocating a page, modifying the data within a page, deleting a page, being able to wrap those operations and any number of those operations in something whereby at any time you can say, oh, now actually revert the database file back to the state it was in before the transaction occurred. Or, if it crashed, okay, we were in the middle of a transaction, let's revert back. So how do we do that? So this project implements a rollback journal. So let's follow through like what that actually is. So if we want to make some sort of mutated change, then what we have to do is we have to call begin transaction. So when we begin the transaction, we open a new file. We create a new file called the journal file. And then we immediately write our root page, which contains our metadata, to that journal file. So one thing in that root page is the actual size of the database file at that given time. So we write that, and that's a page. That's the first position in the journal file. Then, anytime that we want to like modify a page, the caller has to make sure that they called ensure journaled before they actually modify the data. Before, it's very important before they modify it, right? So when they call ensure journaled, what it will do is it will check if in a map, it's like, or in a set rather, okay, have we already journaled this page? If we haven't, then we write that to the journal file. We just append it. Now, because every page that that is worked with the pager has its index in the first 4 bytes of the database or of its actual page. So what is it? So base page. So every page, whether it's a B+Tree node, whether it's a blob node, has the index in the first 4 bytes. We can just, when we modify it and we journal it, we can just append it to the journal file. And because it knows its index in the database file, we can just, like, if we roll back, we can just pick it up and go, oh, okay, this is its position, put it there. So we just append it to the journal file, and now we have the version of the actual like page before any change. So if if it was a free page, if we allocate a page and it's a free page, then it's journaled in there, right? And we know, okay, well, this is position and it was free, and so that goes in the journal file. If it was a page we're modifying, the sort of pre-modified version is in the journal file. And if it's a page that is deleted, we also, we journal it. So, okay, well, this is the deleted page. This is where it went. And so, when we commit, we just throw away that journal file, and we write we first write everything that is dirty in our cache, all the pages that are dirty and need to be written to the database file we do. Then we just delete the journal file, and that's it. That's the transaction over. That's our commit point. But if we want to roll back, then what we do is we say, okay, what's the size of the journal file? We get the first position, okay, offset 0. That's our root, and so we write back our root to the database file, and we make note of how actually big the database file was that our journaled root says. And then we just go, and for the rest of the file, we just read, okay, this page was changed, this page was deleted, let's put it back in its particular slot, right? And then finally, we take, okay, well, the page counter was this, that's what we journaled, times the page size, and truncate the file. So it was back to the size, the whole file is back to the size it was before the transaction started. And that, that will fully revert any changes that have occurred. And then we just sort of, like, in the event of a rollback, for simplicity, I just like refresh the cache, just like clear out everything. So let's actually visualize this from the point of view of the pager. So have a visualization here, which shows all the different like state in the pager. So we have a database file, we have a journal file that exists or it doesn't if we're not in a transaction. We have our root page, which contains metadata like beginning of the free list and the page counter, which times the page size will give us the file size. And then our LRU cache, and then our journal, what pages we've journaled over the course of a transaction, so we don't like journal them again, and including new pages because we don't want to journal new pages. So when we begin a transaction and we allocate a bunch of pages, those are written to the cache, but only the root page is written to the actual journal file. If we allocate more than we actually have cache slots, then some of those will be written to the database file. Then we can roll back, and when we roll back, well, we pull that root page from the journal file. That's the only page in there, and it says, well, the actual size of the journal file just included the root, so truncate it. Just truncate the file, and then you're done, and then you're back to what it was before. And that is, what happened because we just allocated a bunch of pages. We just appended a few. If we and then we delete the journal file, and then we're out. We've rolled back fully. So if we start a new transaction, allocate a bunch of pages, and then commit, then the journal file is deleted, and that is now that our valid our database file in its sort of valid state. If we begin another transaction and delete a page, that page before it is deleted is put onto the rollback journal along with the root. So the new root says, oh, well, the free page is at 3, but the root that is journaled has like, well, no, there's no free pages. And then when we roll this back, our page 3 will be put onto will be put back onto where this free page is now, and the root will be put back, which says, oh, well, there's no free pages, and so that will fully revert that everything that happened in that transaction. We begin one, delete a few, and then commit. Great. Okay, now that's where now we have holes in the database file, but we're tracking them in the root. So now when we begin a transaction and we allocate a bunch of pages like that, now okay, well, these 3 were free, and our page, our actual database file was of a certain size. So when we roll back, the free pages will be put back into their slots, and the root will be the same and pointing to that original, the head of the free page, and then finally the file will be truncated back to the size it was originally, like that. So that's just visualization of the kind the actual transaction mechanism. So it's not that like within the transaction there's some like magical thing that allows you to just make the database valid again, right? It's that at every stage we have a way to get back to our valid state, right? Like before we modify a page, we need to have it journaled so that we can like literally get it back to the state it was before. So like in the middle of a crash, if a database crashes, the database file is messed up, like it is corrupted, but we have the means to uncorrupt it. So like that's what I think sort of transactions like mean. To be honest, I think that sort of makes better like intuitive sense than just sort of like just saying like acid 50 times. You know what I mean? So so that's the rollback journal. So now that we have the pager, we can effectively view the database file as an infinite array of pages, and on top of that, build our specific storage mechanisms for organizing our data. So we've seen that with the blob storage, where we can organize those pages such that most of it is full of like data itself, but then we have just 4 bytes for the actual page index, but then we have 4 bytes also, so we can link those pages together, and so we can group those pages into one blob itself. The other story like data organization mechanism we have is the B+Tree, and this is the sort of quintessential structure that relational databases, SQL databases, use to organize their data. So one table equals one B+Tree. So what is a B+Tree? Well, if you're familiar with LeetCode, probably be familiar with a binary tree where it has the property that if you are on a particular node and searching for a key greater than the key you're currently on, you know that it won't be found in one half of the tree. You don't even need to look there. And so every time you visit a node, you can cut the search space in half. So that's a really good property for like efficient querying, but also binary search queries are good for like inserting and deleting, because when you just have to fix like what the pointers are, like what the nodes are like pointing to, you only ever need to fix a few pointers. Whereas if this was all laid out in an array, and you wanted to like delete an element or insert an element, you'd have to shift everything over, and that can get really, really expensive. So, a binary search tree is, efficient for querying, and it's efficient for actually like mutating as well. So do we use a binary search tree? No, we use a B+Tree. Why? Well, because to do efficient I/O, we want to be working in pages, and if a page is like 4 kilobytes, then just to have one like value in there would be a big waste. So what a B+Tree is essentially is an n-array tree. It is a tree where each node has like n children. More specifically, internal nodes have children, and then the leaf nodes are where the records are actually stored. So in, now that you can't see the records in this visualization, but these internal nodes, we have their keys, and then we have their child pointers. And remember, those child pointers are actually like, they're not like memory pointers, they are indexes into the database file. And then here we have the keys and the leaves, and there would be corresponding records here. And then note also that leaves actually connect to their siblings like left and right, so that if you wanted to do something like a range query, if you wanted to do where ID is greater than 2345, it would be similar to a binary search tree. You would go and you would cut down the search space every time you went to a particular node. In this case, not by half, by by the actual amount of keys in them per node. And so then you could you arrive at the leaf, and then you would just go next, all the way through here, and you would just print that out. And so that hopefully shows like why they're so good at range queries, because they're sorted on something, and you can just go to where the first one it satisfies, and then just go to the end of the tree. So that's B+Trees. Every node, whether it's internal or leaf, is one page. And so that means that when we create a table and we could create the corresponding like B-tree storage for that table, we have to calculate how much stuff we can actually fit in it. So like we saw with VM earlier, where we do this like dynamic like typing stuff, we're like, okay, well, we're creating a B-tree. The key, the like primary key that things are going to be like sorted on, that is going to be, say, a 4-byte integer. So we need 4 bytes for the key. We need 4 bytes for the actual index into that database file for the children. And so that's how much so we need that, and then like it's the page size, the actual available space per page divided by that. That's how many keys we can fit in an internal node. And then for the leaves, it's okay, well, we have the keys, and then we have like the rest of the record. So the page size, the available space divided by the record, the total record size, the key size plus the record. That's how many records we can fit per node. Now this is like a simplification of my like implementation. In a real database, there wouldn't be gaps. Like there's more metadata in the front of a leaf node to say, okay, well, this is how long the row is, and to make sure that there's like there's no space wasted. In my implementation, it's just you say, okay, well, I need 16 bytes for this field, and I need 4 bytes for this field, and whatever. And then that's just like a simple calculation for how much space we need. But yeah, so that is a simplification here. But yeah, we do calculate, okay, yeah, we want, this is the usable space, this is the size of our like leaf entry, and so this is how many entries we could have. So it's just a sort of simple calculation for like that. And then again, we don't have the information up front about what the keys are going to be, and so accessing all of this data is a matter of just doing lots and lots of like pointer arithmetic, casting, and so on and so forth. Getting the data is a matter of saying, okay, well, this is where, because in fact in this implementation, all the keys are stored together, like the keys are stored together, and then the data is stored together. So if we want to get a particular like row, like a the row, we go, okay, this is where the node's like data begins, So we add the maximum keys times the key size. That's where our data, like our actual like record data begins. And then we add the specific index of the record we want times the size of that record. And that's how we get the beginning like memory location of that like data. So it's pretty like it's pretty nasty, to be honest. And this is why like I've just used macros, because like if you try to like debug this and they're all in like, you know, like functions and you have to step through them, but all you can see is a memory address, it's not very helpful. So yeah. And then for things like if you want to insert a key, what you're doing is you have all these keys, and then you want to insert a key. So you basically you do a binary search and find out like, okay, here's where the key should go. Do a mem copy and shift all the keys over, and then insert it in. And if you want to delete a key, it's just the reverse. You go, okay, well, this is the key we want to delete. So what we're going to do is we're gonna like take all the keys like behind it, and then just like do one big mem copy to like shift them over. So yeah, I'm not going to go over like the specifics of the B+Tree algorithm. Like it's here if you want to see it. But yeah, that's the crucial idea. We want to, when we're searching for data, we want to minimize the amount of like file IOs that we do, and that's what the B+Tree is absolutely great at, because when it's searching for the leaf node, where the actual record would be, it's pulling these internal nodes, which are just keys. They're just just a big array of keys, and then with that it can reduce the search space by however many keys that is that is actually in there. So they're maximally efficient in terms of like IO. So I do have a or like I do have some print information about the B+Tree. So here is just logged a B+Tree again to show how wide they are. We have like a couple hundred users or something, or like I think 100 users in this one, and our tree begins at page 2. That's our root. It's an internal node. It has these four keys, these 5 children, and then these are the actual leaf nodes, right? And these are all the keys. These are all the corresponding records. And so when it goes, okay, well, I want I want to find 40, it will just look, is this are we at sort of 40? Okay, go to this one, and then we'll find it. So that's the B+Tree. Really cool algorithm. Yeah. So right now our B+Tree has the following API, right? It has the ability to insert elements, to delete elements, and to find elements. But this isn't enough like for our VM to do all the things we want to do. For example, if we wanted to actually like get all the records greater than a particular value, then we have no way to really do that efficiently. We can seek to this particular key, but then we would need to try every single key like after that, like 2 3 4 6 2 3 4 7 from the root, in order to get all the things greater than it. So like we don't want to do that, obviously. So the solution is to have a stateful way to actually move through this data structure, and that is called a cursor. Now a cursor is similar to your cursor, like your text cursor, right? It provides a few like really like fundamental functions, like for example moving to the end, or moving to the beginning, or moving next, and moving previous, and deleting at where you are in your data structure, deleting that element, or inserting an element there, or updating the element there. Those are the sort of like core operations that a cursor can do, irrespective of the data structure that it is actually like wrapping. So we can build a cursor to move through, move to the beginning, move next, move previous, delete, and then like insert a records in for the B+Tree. Now, what that sort of looks like is something like this, where this is just our 2-level B+Tree, and if we go and we try and seek equal, we'll go and we'll hit 25 here. If we want to go and seek greater than, I think this is or less than, greater than, then we go and we get down to 40, but then we can just call next, and we can call next, and we can call next, and we can call next, and do whatever we want to do with that. Load this record into the VM, do more conditions on it. So we can say, okay, well, get me where the user ID is greater than this, and then for each one of those, you say, okay, where the user ID is greater than 25, and then you pull that in, you do whatever other conditions you want to do on it, and then you just call next, and you call next, and you'll call next. And so that's what a cursor allows you to do. It allows you to statefully move through a data structure. The nice thing about cursor, right, and that the API that sort of a cursor defines, is that it can actually wrap a pretty wide range of data structures, such that you have the same API, but you can actually have different storage backends with different performance characteristics, or different characteristics in general. So this is what we've actually done. Now, I don't know if you thought about how we're actually implementing order by, but the answer is that in addition to our B+Tree, we actually have a fully in-memory red-black tree, which is a balanced binary tree that we can create. And so when we do our order by, instead of just piping out the result when it satisfies some condition, what we actually do is we insert it into this red-black tree by the thing that we want sorted on. So if we want to sort on age, we're going to get that record and we're going to insert it, but have the age as key, and then it's just sorted already. And then whether or not you want it to be output ascending or descending, it's just whether or not you do a pre-order or post-order traversal of that tree when you go and call result. So to see that, we can go bytecode, select a username, age from users, order by age. So this is our program. We open two cursors. We rewind to the beginning of the B+Tree, and we say, okay, is it empty? No, it's not empty. Or if it is empty, jump to the end. Or jump to not the end, rather. We jumped to the program counter where we closed the B+Tree because we've gone through and we've processed all the records, in there. But if we're not at the end, then we load the columns we're interested in. So we have age as the key, and then we have age and username as that's the record, and we insert that into our in-memory tree, our in-memory red-black tree, and then we step forward with our B+Tree. Now we're at the next record, and then we go to program counter 3. Are we at the end? If we are, jump to 10. If we're not, process the next record. And then when we're done with that, and what we do is we close the B+Tree, we go and we rewind, we sort of go to the very beginning of our red-black tree, because in this case it was order by ascending. And then we go and we just call result on our record. And then because we inserted it and with the key is the age, it's sorted. It's already sorted. Sorted. And yeah, this is our in-memory tree implementation. As you can see, for something like group by, for aggregate queries, we can use it. We can use that too. When we want to do, and we saw earlier, where we sort of group by city, what that actually does is we use, we don't allow duplicates. We can allow duplicates or not allow duplicates in our red-black tree. And we say, okay, the key is the city. We're not allowing duplicates. And if you find it in there, get the value, get the record, which is the count, and increment it. If it's not in there, then insert it and set the count to 1. And then you just pipe those out. You just pipe those results out, and there it is. Aggregate queries. Order by, we have order by age. Age is something that more than 2 people are 25, so we need to accept duplicates. So we can just go, okay, here's the age, like insert this, and then insert the corresponding, move to the beginning of the tree, or the end, depending on whether or not you want descending, and then just pipe it out. So we can do that because the cursor interface is the same. They both require, they both have this ability to go to the beginning, go to the end, go next, go previous, go to a specific key, insert in the same way. So yeah, I think the cursor interface is quite powerful, and there is scope. If you're interested to play around with this project, add another storage backend, and try and add like hash storage, right, and make it work with a cursor. It might not make sense to do a range query with a storage backend, but you don't have to. It's just a good interface. Yeah, so that's the cursor. So the last thing I want to talk about is this sort of SQL specific is the actual compilation and things like indexes. So just for reference, an index is a B+Tree where the primary key is a particular column from a table, and then the value is the corresponding primary key, the corresponding key from that entry. And so if you wanted to do something like where age is greater than such and such, then you would look up the index, you would do that efficient seek, and then you would take those now primary keys, and then you would go to the actual table and collect all of those. Otherwise, because our B+Tree isn't sorted on age, it's sorted on user ID, we have no way to know where the ages are, and so we would just have to scan the whole thing. So that's what indexes are. Now, in terms of compiling and creating a good bytecode compiler, we actually we can't just know that there is an index on a particular field. We have to have more information about that index, some actual statistics about that index. For example, with a query select all from users where age is greater than 30, do we use, if we have an index on age, do we even use it? I mean, maybe this table, the population of this table are all pensioners, and they're all older than 30. In which case the index lookup is just pure overhead. We're just going and fetching a bunch of keys that we would have anyway, if we just scan the table. So should we use it? Should we not use it? That's the kind of thing that the actual query optimizer will do. You can go and you can collect statistics. You can go and collect data about the sort of distribution of values in a B+Tree, and then that can go and inform what your bytecode program is actually compiled to. But what we have here, and again, the compiler is the weakest part of this project. But what we have for seek, what we have for select, is if we're doing a condition on the primary key, then we do a seek. If it's a range, if it's a sort of greater than or less than, then we seek to that part, and then we go and we scan to the rest of the tree. So if it's do a less than, we scan to the part, the particular key that satisfies, and then we go previous till we're at the beginning. Similarly, if we're doing greater than, we'll seek, and then we'll just call next until we're at the end. So to show that, we can see that if we do select all from users where user ID equals 40, it's a direct seek. Whether or not we actually found a record, if we didn't, we just jump straight to the end. If we did, we pipe it out, and then we go straight to the end. If we wanted to do select all from bytecode select all from users where user ID less than 40, then we do the seek, and then we find, okay, are we on the thing that satisfies this condition, or are we at the end? If we have something that satisfies that, then we output it, and then we step backwards in this case toward the beginning of the tree. And so that's our query optimization, right? Instead of just going through the entire thing, doing a full table scan, we go, okay, well, we're doing some condition on the primary key. In multiple, if we have a big chain of conditions, we just search, okay, but are any of these on the primary key? If they are, then let's do that one first, and let's do that seek first, and then we know that we can cull most of the some fraction of the table, and we don't even have to consider it. And so that's just the simplest optimization we can really do. But when it comes to, okay, well, now we have indexes, but those indexes, may or may not even be worth visiting first. That's when it can get really, really complicated. So the last part I want to talk about is not specific to SQL, but something that is an important concern when doing a project in, a low-level language, and that is memory management. Now, we talked about how in a low-level language you have to be very explicit about what you do with memory, like how much you want, but more crucially, when are you done with it? When when can you give it back to the operating system so that the process doesn't just require more and more and more memory until it crashes, or so or that you don't free the same memory location twice and then crash because something you thought was live is actually just null. How do you deal with a very nasty source of quite opaque bugs? Well, I've just taken from watching Handmade Hero and Casey Muratori, this idea of a memory arena. So instead of thinking about allocating individual objects, instead of thinking about newing up individual objects and managing each lifetime separately, instead you have arenas which themselves have the particular lifetime. And then when you want to allocate memory for an object, you would pick the arena that lifetime where that lifetime is actually satisfactory for, or if none of them are, maybe you'd create a new arena for it. And then you don't have to worry about freeing that individual object. When you call free on that arena, everything in that arena is just reset, and so it's all sort of taken care of for you. So what's an example of that? And hopefully I've done it right, Casey. But in this, let's think about the lifetimes we have in this project. Well, when we load up and we have certain memory that needs to sort of exist for the lifetime of the program, or at least it's sort of existing between user queries. That's something like the sort of catalog arena. So if we go to catalog, the catalog is the in-memory sort of cache of the master table containing all the schema information. This needs to last between queries, and the only time we reset it is when we in the event of a rollback, we just reload the catalog, right? And so we'll reset the catalog arena, and we'll load everything back up, and then there's that, and then there's on startup, and that's the life cycle. And so I can safely, when I can create add a table, I can allocate to the catalog arena safely, and I don't have to worry about cleaning any of those objects up. So that's one sort of lifetime. Another lifetime is our actual per query lifetime, or more specifically, because we can do multiple statements in a single string. So let's say our user input, single user input lifetime. So there are certain things we need to allocate memory for over the course of that sort of query, of VM execution, what we load, when we allocate memory for parsing into an abstract syntax tree, those nodes, the individual like if it's where age is greater than 5, okay, we need to allocate memory that like 5. For our order by, we need to create this red black tree in order to do the ordering by, so we need to allocate memory for that. But after the query's done, we don't need any of it. It's all garbage. So we can think, okay, well, once our query is done, let's reset everything in the query arena. And that's what we do. So we go to REPL and we go reset, every time the query is done, we call reset and decommit. And that's how we're managing memory. And so we only have a few arenas, and we just everything we do, we just allocate to those. And as long as the lifetime makes sense, then we're we're Gucci, really. So yeah, that was the last thing I wanted to mention, and that is really the last thing in this project worth talking about. So yeah, let me know what you think. Very much open to feedback. I'm not a database guy. I've never worked professionally in C++. So if anyone has any sort of comments as to what could be done better, that other people first and foremost myself can learn from, then please put it in the comments. And yeah, hopefully you find that helpful. So thanks for watching, and yeah.